Welcome back, College Algebra students. We are going to be taking a look at Chapter 6, Section 3 on exponential functions today. Previously, we have looked at linear functions, lines, y equals mx plus b format. We've also taken a look at polynomial functions, functions that are smooth and continuous. We've taken a look at rational functions, functions that have vertical asymptotes and such. And so it's a function where we have a ratio, so a fraction with algebraic operators. Now we want to take a look at exponential functions and identify another category of functions that we can get into. So starting off, what we're going to do as far as our objectives, listing these out, we're going to evaluate exponential functions, graph them, define the number e, and we're also going to solve exponential equations. So before we get into all of this, though, let's take a look at on the graphing calculator, or just on whatever calculator you're using, do we know how to enter exponents? So I've got 3 to the power of 2, 3 to the power of 2.5, and 3 to the power of 4. Now, one way these are written in some type scripts, in some fonts, is we don't have superscripts available to us, so we use the up arrow key or the caret key. It would be Shift 6 on the keyboard, and this would be the way that we would type 3 to the second power, or 3 squared, if we did not have a way to do superscripts. That's important because when we take a look at how to enter this into a graphing calculator, notice we have this caret key here. So if we do 3, this caret key looks like an up arrow, so it means what's coming next should be a superscript, should be the exponent, so we can type that button. Now, on a lot of the newer calculators, newer meaning calculators in the last 5, 6, 7 years or so, maybe even longer, what we have is we have this math print. So it's a very nice feature for us to go ahead, and the math type on our calculator is going to look like what we'd see on our paper. So if we have 3 to the second power, and then we do 3, that caret key, and then 2, and that gives us 3 to the second power. If I went to 2.5 power, so 2.5, type that in, gives us our value. If I went 3 to the power of 4, I can go ahead and do the 4th power. So whatever power we want, we just go ahead and use that caret key. And since we're talking about exponential functions today, we're going to be talking about exponents. So I want to make sure we just had an idea of where that key was located. Now, since we're also talking about exponents, let's do a quick review of the normal rules of exponents. And these normal rules apply whenever the base, or when the base is a number instead of a variable. So if we're familiar with our laws of exponents, if S, T, A, and B are all real numbers, okay, so no imaginaries, and we're dealing with positive A's and positive B's here, okay, and our A's and B's are just our bases. So A is a base, B is a base, S and T are exponents. So a brief overview of our rules here. If I'm multiplying with the same base, I end up adding the exponents. If I raise something with an exponent to another exponent, we end up multiplying those together. If I have an exponent outside of a parentheses, effectively, if this is multiplication, and make sure it's multiplication, then effectively distributes that S through to the bases. 1 to any power, of course, is going to end up being 1. If we have a negative power, okay, negative power here is just going to be the reciprocal. So it's going to be 1 over A to the S. We can write it either this way, or we can write it with parentheses, where either the S is in the denominator, or with the entire expression written in parentheses, the exponent is outside of that. In anything to the 0 power, by definition, is 1. Okay, there is a video in our coursework also that just reviews these laws of exponents with a little bit more detail. So if you want to take a look at those, go back and take a look at Canvas and take a look at that video. There's also a math site just to call to your attention. Its math is power4u.com. And what this has, and I've linked several videos to our course, or from our course to this site. This is a math site that has tons and tons and tons of videos, anywhere from pre-algebra all the way up through calculus. And so if you look just for a short video, and most of the time what they do is they'll just do a short little snippet. So maybe anywhere from 2 minutes, maybe to 8 minutes long, and that's it. Just an example illustrating the topic, and then they move on. But a very, very nice website to go ahead and use that I have found. I've used this website for years. So if you are taking a look at some laws of exponents, you're not quite sure about where some of these things come into play, I've linked a mathsispowerforyou.com video in our Canvas account, and so you should be able to go ahead and find that. So since we're talking about exponential functions, we've been talking about them for the last 5 minutes or so, let's actually identify the definition for an exponential function. So an exponential function is a function of the format f of x equals ca to the x. And notice here that our x is now in an exponent's position. Everything else we've had, x has been the base. Now we're going to let our variable end up being the exponent, because what we're going to do here also is we're going to say that a is going to be a positive real number and not equal to 1. And so if a was equal to 1, then this would just be anything to the first power, 1 rather, to any power is going to be 1. So this would just end up being c. So this would be the constant function. That's really not much to talk about. So we restrict this down that a is not allowed to be 1. And c is not allowed to be 0. So it can be any number except 0. If c was 0, then this whole thing goes to 0, and the f of x is just the 0 function. And so again, not a whole lot to talk about there. So we do lay some restrictions down here. The domain of f then is the set of all real numbers. We can plug any number we want in here for x. The base a here is what we call the growth factor. And because f of 0, so if I let x be 0, that means I plug 0 up in here for x. Then I have ca to the 0. But since a to the 0 is 1, that just equals c. C is what we call the initial value. The other item that we've talked about, whenever we've let x be 0, we've also called that the y-intercept in the past. When we had, for instance, linear format, where we had y equals mx plus b, b was the y-intercept. Because when we let x go to 0, that term goes to 0, and we're just left with b. Same idea here. We call c the initial value, or that's the y-intercept, whichever way we want to reference that. Excuse me. We'll typically refer to it then as the initial value in this case. Now, there are some other ways that we might see this. I've seen other books reference it this way, ab to the x, where b then is our base and a is our initial value. And so we might be seeing it that way, but again, same idea, the base or the growth factor, and then the initial value, either a or c, depending on how it's written. But I want to just call that to your attention. If you take a look somewhere else, they might be listed a little bit differently. So before we take a look at the graphs, let's just take a look at some functions here. And even if we don't know what the graph of a function looks like, we know enough about transformations of graphs that we can identify how these graphs are being transformed from their original parent function. So for example, on f of x here, we have 2 to the x. So we have an exponential here, where 2 is our base or our growth factor, and x then is our exponent. So on this one, we'd have to ask ourselves, are we doing anything to x? No. Are we doing anything to y? Are we doing anything to the 2 to the x? No, we're not. So this is basically a parent function, and so there are no transformations taking place here. There are no transformations to 2 to the x. It's just 2 to the x. Now, different from that is capital letter F here. We've got 1/3 to the x. So that's what our base function looks like here. And we have a plus 5 afterwards. So that means in that plus 5 is how we would have moved the graph up 5 places. So what we have is we have 1/3 to the x shifted up 5 units. Let's take a look now at capital G. So it looks like, the base function here would be 3 to the x, but we have additionally, we have a minus 3 with the x, and we have a multiply by 2 out front. So what we have is we have the base function. We have the base function of 3 to the x, and we have to do the exponents first. Remember, order of operations, exponents, and then multiplication division. So we're going to do the exponent first. So that's going to move, since it's with x, that's going to move 3 places the opposite direction. So instead of 3 places left, it's going to move 3 places to the right. Remember the analogy I've used, if you just broke up with somebody and you have an x, you typically don't want to be around them, so you go the opposite places. So if we have x minus 3, we're going to go, instead of left, we're going to go right. So we're going to go 3 places to the right. This 2 up here, that would be something that we're doing after we have already calculated with x. So that means we're doing something with our y values. So then this is going to end up being a vertical stretch by a factor of 2. And since we have taken a look at other transformations in previous videos, hopefully this ties in together as well. So even though we haven't seen what the graph looks like as of yet, we still can identify, based off our parent function of a to the x, things that are taking place and things that are happening to it. So let's do some calculations with an exponential function. Okay? So let's calculate f of x is 5 times 2 to the x for x equals 0 through 4. We're also then going to identify the constant rate of change between each successive answer. So let's go ahead and calculate some values here. So let's do f of 0. So this would be 5 times 2 to the 0. So this is 5 times 1, so that's going to be 5. Calculate f of 1. That's 5 times 2 to the first. So that's 5 times 2. So that's 10. Some relatively easy mathematics here. F of 2. That means 5 times 2 squared. So that's 5 times 4. So that's going to be 20. F of 3 would be 5 times 2 cubed. So 2 cubed is 8. So that puts us up to 40. And finally, f to the 4th, 5 times 2 to the 4th. Let's see, 2 to the 4th is 16, and that would end up 80. So as we take a look at these, okay, one of the things I want to do is try to emphasize, can we identify how each of these are changing? So to go from f of 0 to f of 1, to go from f of 1 to f of 2, f of 2 to f of 3, f of 3 to f of 4, do we recognize a pattern here? Okay, so it appears as though that we are doubling every single time, okay, which kind of makes sense. If I've got 2 to the 0, that's just multiplying by 1. 2 to the first is multiplying by 2, so I doubled what I had previously. 4 is the same as 2 times 2, so I had 5 times 2 times another 2. 8 is 4 times 2, so I had what I had previously times yet another 2. 16 is 8 times 2, which is what I had previously multiplied by another 2. So anyway we take a look at it, we are doubling each of these. Okay? So our rate of change is 2. And I guess I should say we're multiplying by 2. Another way that we can see that then a little bit as well is we can say, what was f of 1 over f of 0? So if we compare it as a ratio, so if we're doing the rate of change, we need to take a look at the ratio, would be one way to take a look at that. So in this case, that was 10 over 5, which is 2. If I take a look at f of 2 over f of 1, so just successive values here. F of 2 is 20, f of 1 was 10, so that's 2. If I take a look at f of 3 over f of 2, see f of 3 was 40, f of 2 was 20. That's also a change of 2. And if I do, again, successive values, f of 4 over f of 2, then that is 80 over 40, and that's also 2. So by comparing successive values here, we notice we get the same thing. So we have a constant rate of change. Constant meaning it doesn't change. So this illustrates then our next theorem. Our theorem says, for an exponential function, f of x equals ca to the x, a greater than 0, a not allowed to be 1, c not allowed to be 0, so all our standard items as far as our exponential function. If x is any real number, then any two consecutive terms, okay, in ratio to one another is just going to be whatever this constant is as far as a, what we call our rate of growth or our base in this case. Now, if we want to take a look at that a little bit further, we can say if I want to solve this f of x plus 1, if I get rid of this f of x, I can multiply by the denominator. So the denominator just moves over here. So that'd be another way to phrase that. So if I have a current term, if I multiply it by the growth factor, then I end up with the next term. If f of x is the current term, f of x plus 1 is the next term. Now, as far as the proof on this, fairly easy to take a look at. So I just copied this straight from the text when I dropped in the theorem here. F of x plus 1 means that we're going to change the input to x plus 1. So instead of ca to the x, it's ca to the x plus 1. F of x then is still ca to the x. Our c's end up canceling. Our property of exponents, when we divide the same base, we subtract the exponents. So we have x plus 1, which is the numerator, minus x, which is our denominator, and x minus x is 0, plus 1 is 1, so we have a to the first, and a to the first is still just a. So if we want to take a look at any consecutive two terms and take a look at their ratio, once we take a look at their ratio, we know that we're going to end up with that a value, where a represents our growth factor. Okay, so a is our growth factor. Okay, so we've identified parts and pieces of exponential functions. Now let's go ahead and compare that back with linear functions. So linear functions, okay, if we go back and review just for a moment, whoops. Linear functions are the format y equals mx plus b, where m here is our slope. That's the change in y's over the change in x's. So for every so many changes in y, we have so many changes in x, and so forth. When we have y equals ab to the x, okay, then we have our exponential function. Okay, notice again in the linear, x was listed as a base. In the exponential, x is listed as the exponent. Okay, so let's take a look at these and see what we can come up with. Okay, so let's see on the directions. Let's read these through here, and then we'll take a look at the three scenarios. Determine whether the given function is linear, exponential, or neither. For those that are linear, find a linear function that models the data. For those that are exponential, find an exponential function that models the data. So what we want to do then is we'll take a look at these. And so let's take a look at part A first, and we'll see what we can come up with. So as we take a look at the x values, looks like they're all going up by 1. Are the y values changing by a particular amount? So if I would take, for instance, if I'm going to see if this is exponential, I need to compare successive y values and see if they end up being in the same ratio. So if I have, let's see, let's call this y also just f of x, okay, just for ease of use. So f of negative 1, okay, whoops, let me change that. I want successive values. So f of 0 divided by f of negative 1. So if I do successive values, I've got 2 over 5. If I do f of 1 over f of 0, let's see, f of 1 is negative 1, f of 0 is 2. These are not the same values, okay? So that means that we are not exponential, okay? Let's see if we are linear, okay? So linear, we want the change in y over the change in x. So change in y over the change in x. So if I do the first pair here, if I go from negative 1 to 0, okay, what that would mean then, if I take a look at the change in values. So let's do it in order here. We got change in y over change in x. So if I go from 5 to 2, my change is a minus 3, because 2 minus 5 is minus 3. 0 minus negative 1 would be 1. So my rate of change for if I was doing linear would be 3. Let's take a look at the next pair of points. Let's go from 0 to 1. So again, if I take a look at change in y over change in x, from 0 to 1, let's do the y values first. From 2 to negative 1, I went, if I subtract these, negative 1 minus 2 rather is negative 3. And let's see, 1 minus 0 is 1. So that also is a rate of change of minus 3. Let's take a look at the next group. Let's do 1 to 2. So 1 to 2 for the x's would be -1 to -4 for the y's. So -4 minus 1 is -3. 2 minus 1 for the x's is 1. So again, it looks as though we have a linear function. We have the rate of change here. So the average rate of change is constant. So that gives us a linear. So that would be y equals. So our rate of change is -3x. And if we go back up here, we were given our initial value, given our initial value at 0, so that would be our y-intercept. And so our y-intercept is 2. So the function that we're referencing here is y equals -3x plus 2. Let's take a look at letter B. Okay. So one of the things that we might do on these, in addition to what we've just done, is it may be a little more intuitive approach. How am I changing from 5 to 2? Well, I went down by 3. From 2 to -1, went down by 3. -1 to -4, it went down by 3. So that's a constant rate that we're changing. I'm subtracting 3 from each one. Let's take a look at letter B here. And what am I doing here? To go from 32 to 16, I went down by 16. 16 to 8, I went down by 8. Whoop. So I'm not going down by the same thing. So it's not going to be linear. However, if I take a look at this, 32 to 16, I multiplied by half. 16 to 8, I multiplied by half. That's a dot for multiplication, by the way. 8 to 4, I multiplied by a half. 4 to 2, I multiplied by a half. So what we have here then is now we have a common ratio overall. And further then, we have an initial value here of 16. So as we take a look at this one, what we would say then is we have an exponential. So y equals, let's see, our initial value is 16. Our rate of change is a half. And we're raising that to the x power. So we have our initial value. And then our growth rate, okay, which in this case is that common ratio. Okay, so if I write these numbers over top of each other, 32 over 16, okay, would be 2, 16 over 8 is 2, 8 over 4 is 2, 4 over 2 is 2. So I have that ratio. Now, as I take a look at consecutive values, though, I reverse that. I would really do 16 over 32, 8 over 16, 4 over 8, 2 over 4. So my ratio is 1/2 here. So 1/2 is my growth factor. And as I take a look, as I keep increasing with values of x, my y values keep getting smaller because they're being multiplied by half of what I had previously. As we take a look at letter C, okay, let's see, if I just take a quick look here, if I'm taking a look at ratios 2 to 4, I multiply by 2, 4 to 7, I'm not multiplying by 2 again, so this is not going to be exponential. Let's see if we're changing some other way. So 2 to 4, I can say I added 2, 4 to 7, we added 3, so that's not going to be a linear either. So in this case, that one's neither linear or exponential. Because for the linear, I need to be adding or subtracting the same amounts all the time. And for the exponential, I need to be multiplying or dividing by the same amount all the time. Okay, so a couple different ways we can take a look at those as far as what's the difference between these different pieces. Okay, all right, so we've talked about the exponential function a fair amount. We have yet to go ahead and take a look at a graph. So let's do that. Let's take a look at a graph. So let's graph the exponential function f of x equals 2 to the x. So every other time when we've been plotting points, we have taken a look at some very common points to use. So we have x and then 2 to the x. So let's do -2, -1, 0, 1, and 2. Those are the 5 points that we have very consistently used throughout our course whenever we have a new function. Why do we choose these values? We tend to use these values for the simple reason that they are easy to use and easy to calculate. They are right next to our origin, so they fit on our grid well. So that's the reason why we choose these. Okay, so let's take a look at these values. So we get 2 to the x means 2 to the negative 2. The negative power means take its reciprocal, so 1 over 2 squared. So that makes it 1 over 4. I'm going to need to spread these out a little bit further. So at negative 1, I have 2 to the negative first, which means 2 over 1 to the second, which means we have 1/2. At 0, we got 2 to the 0. Anything to the 0 power is 1. At 1, we have 2 to the first, which is 2. At 2, we got 2 squared, which is 4. So as we try to graph these, let's see what we end up and make this a little bit bigger here. At negative 2, we're 1/4, so fairly small, close to 0. At negative 1, we're 1/2. At 0, we're 1. At 1, we're 2. And at 2, we're 4. Now, if I did 3, 2 cubed would be 8. And the negative third would be 1/8. Notice a particular pattern here. We have the negative second and the second. We have 1/4 and then 4. Negative 1 and 1 are reciprocals of each other, and then we have our base here at 1. So our graph is going to be really high up here, going to be coming down, and then we're going to start hugging the x-axis because we're hugging 0. So as I keep going in this direction, if I keep going left, okay, I'm going to end up with 1 over 2 to the 4th, 1 over 2 to the 5th, 1 over 2 to the 6th, 1 over 2 to the 7th. Those numbers are going to get really, really close to 0 very, very quickly. Okay, so what that tells us then, okay, overall, is that as we go left, we end up with a horizontal asymptote. We have a horizontal asymptote here at y equals 0. Okay. Additionally, one of the things just to note, at negative 1, okay, negative 1, 0, and 1, so 3 key points here to take a look at. At negative 1, we're the reciprocal of our base. At 0, we are the base. I'm sorry, 0, we're 1 rather. And at 1, we are the base. Okay? So at 0, we're always going to be 1. Negative 1/2, we're going to be 1 over our base. And at 1, we're going to be our base. If we had the function, if our function was y equaled ab to the x. So that is one thing that we could take a look at. At negative 1, 0, and 1, we would end up with this kind of idea here overall. Okay. Oops, not if we just have b to the x. Let me be a little more careful, not the a. We don't have any multipliers in here just yet. Okay, so that's our general shape of our graph, and so we're going to end up. Let's see. Let's talk about our domain and range here. So our domain. Our domain here, we can choose any values for x. If we take a look on the x-axis, any value we want. So went from negative infinity to infinity. In our range here, okay, since we have an asymptote, we're going to go from 0 up to infinity. Okay? And we're not going to include 0 because we never actually got to 0. We're going to get very, very close, but not quite there. Okay? Now, one example of an exponential growth might be Amazon's revenue between 2000 and 2017. If we take a look, if this was linear, it would do something of this sort. As we take a look, if we kind of follow this path along, it's shaping up like the exponential function. Okay? So this is just an example of how the exponential function could look. A lot of financial applications end up using our exponential growth features. If we go ahead and invest money over time, this is why retirement accounts are so important, particularly for our younger population as they first get out of college or first out of high school and they start saving money. As we save money in retirement, for the first several years, it doesn't seem as though we're accumulating much, but as that time progresses, then it goes up higher and higher. So say, just for instance, if we ignore these values here, if I start at age 20, maybe by the time I'm age 60, these keep going fairly large, so maybe a span of 40 years here. But if I don't start saving until I'm 30, then I don't see this value out here until I'm 70. If I don't start saving until I'm 40, I don't see these values out here until I'm 80. So the earlier we can start saving money, the better off we are. So just a sidelight on that one as far as what that example looks like, but that's one as far as where that comes into play. Now, the other bad part about this also is this could be our debt as well. Okay, if we don't pay off our credit card statements every month and they just keep slowly building and building and building, eventually they just grow astronomically quickly, and it's very easy to get behind on those. So that's why it's very, very important from a financial perspective to go ahead and make sure early on we're paying off all those credit cards very, very consistently. So I'm not a financial advisor, I'm just a mathematician, and I recognize some of the mathematics behind things. So all of that stuff, please don't take any of this as financial advice. I'm just talking about the mathematics that's involved. Okay, so a little caveat there. So properties of our exponential function overall. We've already taken a look at these primarily, but let's formalize those. These are the properties that we see all the time if we just have a to the x. Okay, so if we have a to the x where a is bigger than 1, what I am used to very consistently, one book I taught of or out of for a number of years used b instead of a. This particular book uses a instead of b, so I will reverse those very, very consistently. The idea, though, is whatever our base is, that is a key piece there. So whether we call it A or call it B. In this case, I think, because previously I called it, up in here, I called it 1 over B, okay? And B to the x. Our textbook here calls it A, okay? So similar type items, just to call that to your attention. So the domain is a set of all real numbers from -infinity to infinity, and the range is the set of all numbers from 0 to infinity, because we do have this horizontal asymptote that's listed down here. The x-axis is the horizontal asymptote. So as x approaches -infinity, as we go to -infinity, this graph is going towards 0. So as we go to the left, it goes towards 0. Now, one of the things we'll see in a few minutes, if I take the reciprocal of this base, then it's going to go ahead and come down something like this. Okay, actually, let me do it this way. It'll be down like this. Okay, and as we go to the right, it will go ahead and go towards 0. But the idea is that we will have this horizontal asymptote. Additionally, there are no x-intercepts. Okay, because when does this go to 0? So if I have that value, when does 0 equal something to a power? Well, if I take a to any power, the only way I can get 0 out of that, and that's a 0, not a 6, let me clean that up. The only way I can get 0 by multiplying is if I multiply by 0. And since a has to be by definition or by requirement but larger than 1, we never end up with that happening. So there will never be, as far as the parent function a to the x, there will never be an x-intercept. The y-intercept, however, if I have the y-intercept when x goes to 0. So when x is 0, this is a to the 0, okay? So we have a to the 0, which then, of course, is just 1. Additionally, this is an increasing function. So a to the x, if a is larger than 1, is an increasing function. So it keeps getting larger and larger. What we've seen previously is if a function is if it's strictly increasing, that makes it 1 to 1. The interesting thing about being a 1 to 1 function means that we could be able to find an inverse. So we'll find an inverse in one of our later sections. We're not going to do the inverse today, but we will have an inverse later on. And the graph contains these 3 specific points. We'll have -1 and 1 over a. We'll have 0 and 1, and we'll have 1 over a. And if we think again about what we're doing here, this is the exponential function, a to some power. So if our power is -1, we just take the reciprocal. So that's what this is going to be. If a is 0, we have a to the, if a to the 0 power rather, then we have 1. And if our exponent is 1, then we have a to the first power, which is just a. Okay? And that thing will happen very consistently for us. So what if instead of having, in this case, we did f of x equals a to the x where a is larger than 1, what if a is less than 1, like we have down here at the bottom of the screen where we have 1/2 to the x power? Let's take a look at this graph and see what we end up with. So we're going to do the same thing that we had done previously. Let's go ahead and take a look at some x, and then we'll do 1/2 to the x power. So let's do -2. So that would be 1/2 to -2nd power. But a negative power tells us to take the reciprocal. So the reciprocal of 1/2 is 2. Now take the squared, so that's going to be 4. Negative 1, so we have 1/2 to the negative 1. Negative power says to take its reciprocal, so we have 2 to the first, so that's 2. Let's do 0 for x. So we got 1/2 to the 0 power. Anything to 0 power is 1. If I do 1, I've got 1/2 to the first power, which is 1/2. And with an x be 2, then we have 1/2 squared. So 1/2 times 1/2 is 1/4. Again, notice some similarities here. At negative 1 and 1, we are reciprocals. And at 1, at 0 rather, we are 1. And we have reciprocals also at negative 4 and 4 and 1/4 when x was negative 2 and positive 2. So on our graph here, let's see, at negative 2, we're 4. At negative 1, we are 2. At 0 is 1. 1 is 1/2. 2 is 1/4. As we kept on going, we get 1/8, then a 16th, etc. So those are going to start hugging the axis here like we did before. And the negative third power then would be an 1/8. Negative fourth would be 16. So that's going to keep going up that way. So it looks as though we have a very similar graph. So previously, our graph looked like this, and now we've basically flipped it over the y-axis. And so as we take a look at this one again, let's identify a few key pieces here like we did previously. So our domain when our base here is less than 1, again, was all real numbers. So we go from negative infinity out to infinity. Our range, okay, how high and low do we go? It looks as though as we go out to the right, we're approaching 0 as far as the function. So 0 is a horizontal asymptote. So horizontal asymptote at, oops, I'm going to say x equals 0. Let's do y equals 0. That means we only go from 0 on up. So our range is 0 to infinity. And notice again some key pieces here. At negative 1, we are the reciprocal of our base. At 0, we're 1. And at 1, we are the base, just like we had previously. So I'll come back to that other visualized piece in just a moment. So when we have our base here, a to the x, is between 0 and 1. Okay, then again the range, or excuse me, the domain rather, is all real numbers, and our range goes from 0 to infinity. So the domain and then the range. Just like, so that piece is the same whether a is less than 1 or whether a is larger than 1. There are no x-intercepts, and the y-intercept is 1, just like we had previously. The x-axis, y equals 0, again, is a horizontal asymptote, just like we did previously. Now, instead of being increasing, we have a decreasing function. If we're decreasing, that also means it's 1 to 1, which also means that we can find the inverse function. Same set of 3 points here. We're going to end up with negative 1 and 1 over a, so negative 1 and the reciprocal, 0 and 1, and 1 and the base. The graph is smooth and continuous with no corners and no gaps. Okay, so we go ahead and we have our graph there. What I'd like to do is let's come back up here and take a look at our graphing calculators or Desmos or whatnot, and let's take a look just briefly at these things side by side. So if I would take a look at 3 to the x and then 1/3 to the x, what's the change in these? How do these look? So let me grab my graphing calculator here. Clear those back out. So let's go to y equals, and let's say that's from a previous item, so let's clear those out. So we want 3 to the x. So let's do 3 to the x. And then let's also do, I'll put this in parentheses, 1 divided by 3. Also raise that to the x. So 3 to the x is in blue. 1/3 of the x is in red. Let me do my window here. Let me do zoom standard, so number 6. So I'm not sure where my window was previously. Okay. So what we have here then, our blue function was 3 to the x. Our red function was 1/3 to the x. So notice in our blue function, we keep increasing. So if my base here was 3, and so if I have x to the 0, I'm going to be at 1. But at 1, I'm up here at 3. At 2, I'm going to multiply by 3 more, so I'm going to be up here at 9. At 3, I'm going to multiply by 3 more. So if I have 3 as my base, as I consistently go farther to the right, I'm going to get bigger because I keep multiplying by 3, because the exponent means repeated multiplication. Likewise, if we have this red graph is 1/3 to the x, so for every time I keep going to the right by one x value, I multiply my y value by 1/3, so I keep getting smaller and smaller and smaller. That's why anything with a base between 0 and 1 is going to what we call exponential decay, because we're slowing down here. And if our x is bigger than 1, not our x rather, our base is bigger than 1, then we're exponential growth, because we keep getting larger and larger and larger. And so that's one of the things that we will see very consistently. Now both graphs over here, now let me go ahead and do the trace coming in here. So I'm on the blue function here. At 0, I'm at 1. As I go towards 1, might not land on there exactly, but I would be really close to 3. Okay. As I go down over here to -1, I should be really close to 1/3. Okay, which is about 3, 3, 3, 3, 3, 3, etc. If I go ahead and switch graphs and switch to the red functions, just up arrow here, if I'm at -1 or really close to that, then I'm at 3, which is my base. If I'm at 0, I'm going to be at 1. If I'm at x equal to 1, I should be at my reciprocal of the base, which would then be 1/3. It's about 0.333. So we see that we're really close to that. Okay. Now I could technically go up here and have to calculate and get values here. So when the x value is 1, okay, I'm up there at 3. When the x value is 2, I'm up there at 9. At 0, we're 1. At -1, whoops, I hit -1 instead. Sorry about that. Let's go back through there. I hit -1. I went -1. There's a difference in the graphing calculator. Notice this minus is slightly smaller and bigger. If I hit the minus key, it's a little smaller and longer. Okay, so that does change. So we'll make sure we hit the negative key. So at -1, now we see more so we are indeed at 1/3. 1/3 as a decimal is 0.3 repeated. And the other thing to take a look at then is that if we have y sub 2 is 1 over a to the x, that would be the reflection about the y-axis of a to the x. So these values do flip-flop. Let me bring this back up over here. Notice these values flip-flop across the y-axis. The y-axis is the axis of symmetry in this particular case. Okay, so let's move on here. Let's now graph a function and see what we can come up with. So we're going to graph a few here realistically. So let's take a look at f of x is 2 to the negative x. So 2 to the negative x minus 3. Okay, so we've got some interesting items going on here. So let's see. So our parent function, okay, so our parent function would be f of x is 2 to the x. Okay, so that's our parent function. Let's take a look at our transformations and see what's taking place. So the negative in front of the x, okay, what's that going to do? That's going to flip it over the y-axis. Okay, and then we have the minus 3. The minus 3 here is going to go ahead and shift us down. So that's a vertical shift. Down by 3. Okay, so let's go ahead and do some graphing here and see how things change. Let's take a look at x, and then we'll do our 2 to the x, and we'll see how things change as we move along. So if we have x, let's do -2. So that would be 2 to the negative second. That's going to be the reciprocal, so that's going to be 1/4. At -1 is the reciprocal of 2, which is 1/2. At 0, we know is 1. At 1 has to be the base. And at 2, we're 2 squared, which is 4. Okay. So now let's go ahead and let's do a transformation. Let's do x, and let's do 2 to the negative x. Okay. So what we're going to end up doing, if I take the opposite of my x value, this should be the flip over the y-axis. So now I should have 2 is going to, excuse me, yeah, so 2 now is going to end up being 1/4, because now I've got 2 to the negative 1/2, so 2 will be a fourth. 1 will be a half, because now I'd have 2 to the negative 1. At 0, of course, is still going to be 1. 1 then, whoops, 1 then is going to be, whoops, did I reverse that? 2 to the negative 1 is going to be 1/2. Well, I think I made a mistake here. Let me go back and double check this. So 2 to the negative second, so that would take the reciprocal. Oh, yeah, I'm sorry. I wanted to flip-flop these. Yeah, because we're doing 1, and then we're flipping over the axis, so I went -1. No, I was doing this right. I just forgot what I was doing down here at the end. -1 and -2. So at 1, it's going to be -1 rather, so 1's now going to become -1. 2 to the negative of -1 is 2 to the first, which is 2. That makes sense, because what we're doing here is we're showing how this point here, 1, 2, becomes the point -1, 2. Okay? Kind of slipped into neutral there for a moment. Sorry about that. So if we plug in -2 up here, 2 to the negative of -2 means 2 to the second power would be -2 then, and the point 4. So that flipped then. That flipped over the y-axis. And now, let's see, if we have our x values, and we have 2 to the negative x, and then we wanted our, whoops, -3. Okay. Let's go back here, take a look at our function up here in the top left. Okay, so f of x is 2 to the negative x minus 3. So just 2 to the x is going to be this first set of tables. 2 to the negative x is going to go ahead and reverse, and we're going to flip over our y-axis. So the x values switch signs, the y values stay the same. Now what we want to do is we're going to plug in this -3. So my x values are going to stay the same. And I'm going to change on my y values by subtracting 3 from each of those. So this is going to be shift down by 3. So instead of being at 1/4, if I shift down by 3, now I'm at -2 3/4. At 1/2, if I shift down by 3, now I'm -2 1/2. 1 shift down by 3 is -2. 2 shift down by 3 is -1. 4 shift down by 3 is 1. Okay? So we have those values. Now we can go ahead and graph. So one of the things just to note on some of our concept checks is on our concept checks, we are asked to show some work when we're doing our parent transformation, something like this. This work here is the work that's being asked for on those concept checks. So if we're asked to show the table or show the work that that shows the transformation, this is how we could go ahead and show that transformation. Okay, so let's now go ahead and do our graph. So let's see. Now, our parent graph normally has an horizontal asymptote here at 0. Since we shifted down by 3, our asymptote here should be at y equals -3. Okay, so we have a horizontal asymptote at y equals -3. Let's see what other values we go through then. At 2, we're -2 3/4. So 2, we're -2 3/4 down over here. At 1, we're -2 1/2. At 0, we're -2. At -1, we're -1. At -2, we're +1. And so our graph would go up like this and then come down over this way. Now, if we kept this on going, then we could go ahead and move this up a little bit more steeply as we go. So that would be our basic graph. If I went ahead and did -3 here, let's go ahead and plug in -3. So that means 2 to the power of 3, which would be 8, minus 3 would be 5. So at -3, we would be 5. So that's up here. So if I was trying to be a little more accurate as far as moving that up, it would look something like that. Okay. So when we take a look at then at our domain, again, our domain has not changed. We can still use any value for x that we want. Our range here, though, our range has changed. Normally, our range goes from 0 to infinity. But now we've moved our horizontal asymptote down to -3. So our range is going to change now. Instead of 0 to infinity, it's going to change and go from -3 to infinity. Our y-intercept normally is at 1. But in this case, we moved it down 3, so 1 minus 3 is 2. So down -2, and that's what we had over here in our table at 0, -2. So we can see the base functions here as far as what they're looking like overall, and that's the graph of an exponential function. Okay. Now, another way that we could have done these, let me just show this as a separate technique here. If we're just interested in getting a graph, we're not necessarily concerned about showing all of the table. If we just take a look at the graph, and we want 2 to the negative x minus 3. Well, if we just graph 2 to the x, okay, so 2 to the x must go through, it's like 0, 1. 1's going to be 2, 2's going to be 4, 3 would be 8. At -1, we're a half, -2, we're a fourth, etc. So this would be, this graph here is, this graph here is 2 to the x. If I want to graph 2 to the negative x, that flip-flops it over the y-axis, so I have the symmetry. So over here, instead of being at 3, 8, I would be at -3, 8. Instead of being at 2, 4, I'd be at -2, 4. Oops, I went -4, 8 instead of -3, 8. At -1, I would be at 2. At 0, I'm still going to be at 1. At 1, then, I'd be at a half, and then at 2, a fourth, 3, and an eighth. So this would be my graph if I'm doing 2 to the negative x. Remember what a negative power does for us? It takes the reciprocal. So 2 to the negative x is the same as 1 over 2 to the x. So we see that decay function coming along through here. And then if we do our subtract 3, well, every one of these points goes down 3. So this -3, 8 comes down 3, 1, 2, 3, down here to 5. This 4 comes down 3, down here to 1. This 1 comes down 3, 1. Oops, did I miss a spot there? Oops, yeah, this 2 comes down 3, 1, 2, 3, down here to -1. 1 comes down 1, 2, 3. This one comes down 1, 2, 3. This one comes down 1, 2, 3. The y equals 0 as an asymptote comes down 3 also. And so this is the same graph that we had just completed. Let me make it go just here a little bit quicker there. That's the same graph that we had just done by doing our tables. And so we do end up with those same values. So depending on what our requirement is, if we're just interested in the graph, then yes, we can do the tables, but I like to go ahead and graph the parent function and then slowly transfer and transform the graph along the way and see where things go. Okay, so the personal preference as far as if you're asked to show the work specifically, then we'd want to go ahead and do all the tables. If we're just asked for the graph, then we end up with this one over here. So in the, I guess this orange color here, that's when we end up with f of x equaling to 2 to the negative x minus 3. So that was that last graph there. When we get into our exponential functions, there is another common element that comes up, and that's the number e. So I'm assuming in high school geometry somewhere we've seen the letter pi or the number pi, and so pi is the ratio of the circumference to the diameter of a circle. If we think about the rate or the formula for circumference, it's 2 pi r, but 2r is diameter, so that's pi d. So if we solve for pi, it's circumference divided by diameter, and pi roughly is 3.14159, and it keeps on going and going and going. So pi is what we call an irrational number, and we use a symbol for it. We use a Greek letter, pi, and that's an irrational. It's a number that doesn't, as a decimal, does not terminate, so it doesn't stop, and it doesn't repeat either. We have another irrational number, and the other irrational number that we're going to reference now is the letter e. So the number e is defined as the number that this expression goes to. So if we take 1 plus 1 over n to the n, so we have an exponent here. If we let n get really, really, really large, so if we let n go towards infinity, So in calculus, we would express it this way. The limit as n gets really, really big. So where does the function go to? Where does 1 plus 1 over n to the n go to as n gets really large? We define that as e. Okay, so it comes from a mathematician whose last name is Euler, E-U-L-E-R, okay, German mathematician, if memory serves correctly. And so since Leonhard Euler was a mathematician who formalized this thought, the number is named after his last name, and his last name begins with the letter E. Now, we have this in our calculator. This number comes up. This is the natural growth number, okay? And so the natural growth rate. And so things very naturally just grow at this value. So trees, plants, things in nature, a lot of items have this particular rate of growth. If we take a look at our calculator, oops, let me go back to regular calculator here. We do have an E button, okay? So we have an E button up here next to the division key. So if I hit second and then E, and it tells me that number is approximately 2.718281828. Now, this looks like it might be repeating 281.828, so 828.1.828, but out here it doesn't keep repeating. Okay, so the values change. If we had a larger display, we could see some more values. Okay, but approximately 2.7 is where that is. Now, another thing we can do to find that, we press the second key and then this ln. That's not an I, that's a lowercase l. So, and then that gives us e to the x. So if we want to raise it to a power, so if I want to take it to the second power, so e squared is going to be about 7.38. Okay, so what is our value for e equal to? It's about approximately 2.718. So let's go ahead and write this in here. So it's approximately equal to 2.718. So not exactly, but close enough. Kind of like pi. Pi isn't exactly 3.14, but for most of our calculations, that is close enough as far as where we want to go as far as our values. So what we will see as far as graphing these exponential functions is we can graph with base e also. So let's graph negative of e to the x minus 3. Let's determine its domain, range, horizontal asymptote, and the y-intercept as well. Now, one thing just to note, when we do this in my math lab, so our homework platform through Pearson, one of the things that we'll see when we do the exponentials, there should be a template that shows the exponential template, and you go ahead and you can click on, I believe, the base for E, and it'll go ahead and snap in place. Then we'll have buttons and sliders that will allow us to go ahead and move horizontally shifts, vertical shifts, and whatnot. Okay, so we'll have all those items along the way. So our parent function, okay, if we take a look at this, our parent function is just going to be e to the x. So when we do, let's see, we do the order of operations, we'd have x minus 3 first. So that minus 3 is going to shift 3 to the right. Remember, our anytime we work with our x's, we go the opposite direction. Then when we have negative e to the x minus 3, that's going to be a flip, and that's going to be a flip over the x-axis. Okay. Remember, if we think about x squared, go back to a function that we're familiar with. X squared looks like this. Negative of x squared flips over the y-axis and goes down. So we're going to do the same thing here with our parent function here with e. So as we take a look at some of these components, let's create a little table here. And we'll do e to the x. So we'll do, let's do negative 2, negative 1, 0, 1, and 2. So this would be, let's see, e to the negative second, so that's going to be 1 over e squared. Then we're going to end up with 1 over e, with 0, e, and then we'll end up with e squared. So we would end up needing to figure out some values on these things before we do anything else. Then let's do 3 to the right. So if we shift 3 to the right, that's going to change our x value. So we're going to add 3 to each of these. So negative 2 becomes 1. Negative 1 becomes 2, 0 becomes 3, 1 becomes 4, and 2 becomes 5. My other values stay as is. Whoops, not 0, it's not 0, 0, it's 0, 1. My mistake, there should be 3, 1. Anything to 0 power is 1, not 0. Common mistake, just be careful about that. And then we would have, e, and then e squared. And then let's flip over the x-axis. So if we flip over the x-axis, this was also the minus 3 up top. So this is going to be e, so negative e to the x minus e, or minus 3. So really, in the order of operations, it is e to the x minus 3, and then the negative out front of that. So let me be a little clearer here as far as notation. Notation-wise, it is this. Okay, so this is what we're doing. So what that's going to do, if I flip over the x-axis, that's going to change all my y values. So my 1, 2, 3, 4, and 5 stay as is. I just take the opposite of my y value. So it's going to be 1 over e, negative 1 over e squared, negative 1 over e, negative 1, negative e, and negative e squared. Now, one of the things we'd want to do then is just type these into the calculator and see, well, what are these values? Okay, and so let's see these. So we know E is approximately 2.718, so let's call it negative 2.7, just roughly. And so now we're going to have to do some calculations here. So let's take a look at these. So I've got 1 over, and I want E squared, so I'm going to do E squared, so I've got E to the second power. So that ends up being approximately, oh, and I wanted this to be negative also, so I just put the negative out front. Negative 0.14, and then negative 1 over e. So let me take 1 over, so 1 divided by, we'll do negative e here. So that's going to end up being, what do we say, about negative 0.37. At negative 1, we're saying negative 1, about e squared, the negative of e squared. Okay, well, I think, let's see. Yeah, so we already had e squared earlier just by accident. I didn't intend that, but that's what it was. So that's going to be about negative 7.4. Okay, so while I was reading those numbers off, I was actually writing them behind that screen over here. So now we have these values as well. And we can go ahead and take a look at these and see where our values lie. So at 1, we're going to be negative 0.14. At 2, negative 0.37, so a little lower. At 3, we're negative 1. 4, negative 2.7. And at 5, negative 7.4. It's going to start going down pretty rapidly. Oops. So we're going to do something of this sort. And so as we take a look at that, my y-intercept here, there's not my y-intercept, but my horizontal asymptote here, y equals 0, still stays the same way. So if we take a look at our domain doesn't change. It's still negative infinity to infinity. Our range here, okay, we did not shift it up or down, so it's normally then that would be 0 to infinity. But since we did flip over the x-axis, we go from negative infinity now up to 0. So as low as negative infinity, but as high as 0. Our horizontal asymptote, y equals 0. And let's see, our y-intercept. So when, let's see, when are we going to have our y-intercept? So at 0, so let's see here, if I plug in 0, we've got negative e to the 0 minus 3. So that's negative of e to the negative power of 3. So I'm going to have to take a look at that on the calculator here. So that is negative of e to the power of negative 3. About negative 0.05, okay, ends up being what our y-intercept would be then, okay? So we have all of those, and we've listed our values here. We were asked to list all of those, and we were successful. Last concept overall with our exponential functions in this particular section, we're solving exponential equations. So if we want to solve equations that involve exponentials, okay, so exponential functions, so I have one exponential set equal to another exponential. So equations that involve terms of the form a to the x, where again our platforms or requirements stay the same. A has to be bigger than 0 and a cannot be 1. We refer to these as exponential equations. We can solve them with the law of exponents, one of the laws of exponents. Now our book referenced that as property number 3. Basically what it says then, if a to the u is a to the v. So if our bases match, and these things are equal, the only way that can be true then is if the exponents are also equal. So if our bases are the same, then our exponents we can set equal to each other. Okay, so what does that do for us then? Okay, so let's take a look down here at letter A. If I have 3 to the x plus 1 equals 81, I need to try to get my bases to be the same. Okay, so I can't do anything to the 3. That's still just going to be 3. But 81, however, if I write this in prime factorization, let's see, that's 9 times 9. 9 is 3 times 3 for each of those. So 81 is the same as 3 to the power of 4. So I can rewrite 81 as 3 to the 4th. Now what I have is I have my bases are the same. So if my bases are the same, that means my exponents now have to be the same as well. So that means x plus 1 must equal 4. So x then must be 3. We can do the same thing over here with our letter B with our bases 4 and 8. Now I can't make these the same as far as 8 is 4 to some power. It doesn't quite work that way nicely. So what we would say is let's break both of these down, because both of these can be broken down to 2. So we say 4 is 2 squared, and 8 is 2, 1, 2, 3, 8 is 2 cubed. So I can rewrite this, instead of saying 4 to the 2x minus 1, I can say it's 2 squared to the 2x minus 1. And instead of 8, I can say it's 2 cubed to the x plus 3. So now my bases are the same, so that means my exponents now have to match each other. So I've got 2, and then 2x minus 1 has to equal 3, and then x plus 3. So now we have a big distributive property. Whoops, I said distributive and then forgot to distribute. So that's going to be 4x minus 2, and then 3x plus 9. If I subtract 3x from both sides, I get x minus 2 is 9. If I add 2 to both sides, then I get 11. So x ends up being 11. Okay, so that last little bit here, solving the exponential equations, what we need to then do is, if we don't have the same base, use this idea of the prime factorization and do the factor tree, break it on down. What we should see then overall is that both of these numbers, like the 4 and the 8, they both reduce down to 2's. Over here with the 3 and 81, they both reduce down to 3's. Now, if when they reduce down, they don't reduce to the same number, then we have to use another technique called logarithms, and that is one of our future sections. So everything that we do in this section, those bases will reduce down to the same number if we put them in prime factorization. Okay, so that's the thing that we'll need to do. We have now concluded Chapter 6, Section 3 on exponential functions. We've identified what the exponential functions look like. We've graphed them. We've defined at the end the number e, and we've also very quickly we solved exponential equations. So as always, if you notice a mistake, please go ahead and get a hold of me and let me know. Otherwise, I will see you in another video.